Thank you, Dallas. Well, I don't know how dynamic it can be when we've got it next to the microphone. So, as Monty Python says, and now for something completely different. How do I change the slide here? That works. I've not been involved with geology at all, basically, since that paper. I've gone off in a completely theoretical way, and there's very little real data in this talk. So you should, those of you who are expecting to hear some new revelations about geology will be disappointed, I'm afraid. What I'm going to really do is tell you something that you all already knew, but didn't know you knew it. The idea is to look again at some fundamental, profound assumptions that everyone makes and never questions, and never realizes they were making those assumptions. And I was going to make a much longer talk than this with a lot more math in it, but as Teddy Bullard said, never integrate in public. Which is a great catchphrase. Well, I devoted a lot of my life to, my academic life, to inverse theory. One of the problems about inverse theory is, about inverse problems, I should say, is that you very rarely, if ever, have any practical, effective uniqueness. Uniqueness means that if you have a model, it's the one and only model to do the job. Now, when it comes to magnetic anomalies and crustal magnetization, it's well known in mathematical circles that there is no uniqueness. That you can have perfect and exact magnetic field measurements around a body, and there are infinitely many wildly different models of magnetization that will fit that data. And so when you say, I've got this magnetic anomaly, I'm going to tell you what the magnetization is like inside the body, you're talking nonsense, because it cannot be done. There are just infinitely many different solutions. Now, you would say, well, that's just a lot of mathematical pedantry. Who's interested in that? Can't possibly affect us in earth sciences. I mean, we know what's going on. Well, I'm going to give you an example in a minute, but before I get to that, I want you to think about gravity data. Gravity data is the same non-uniqueness. Potential field data are basically all the same. And there are infinitely many different, wildly different density models that are consistent with a given set of gravity data. Well, you say, well, I should say you could write a rather big book about the mistakes made using trying to interpret gravity data. For example, Teddy Bullard again, one of his first major papers, used gravity data over the Kenyan rift system to show that there was a compression feature. And Malik Taiwan, as you'll know, thought he proved that seafloor spreading was wrong from gravity data of bridges. There are plenty of reasons for realizing that the non-uniqueness of potential field data has a serious effect. Now, so, onward. How you get round the problem, in fact, that there are infinitely many very different models of magnetization structures that are consistent with magnetic field observations? Well, the answer is, as in all subjects, in all science, you have to make some assumptions, simplifying assumptions. You start with a model that simplifies things and sweeps under the rug all the complications of real geology and real rocks. And so that's what everybody does. And so Fred Vine had this brilliant idea of saying these stripes are caused by the reversal of Earth's magnetic field, and we can make a mathematical model for that to match the observations, to match observations with a hypothetical set of magnetization, with a hypothetical crustal magnetization. And so he introduced this, what you have to admit is the oversimplified model of a set of normal reversely magnetized blocks in great parallel echelon like that. But that was the underlying thing, the underlying model for interpreting seafloor spreading anomalies or magnetic anomalies. Well, I'm going to. This is one of my there's a model that exactly that kind, which I was involved in publishing. You can see the model and the theoretical magnetic anomaly, and you see the data. They don't fit very well. But everybody said, well, of course, yes, that just proves that the crust is just like that. Then the data there were from the North Atlantic, 45 degrees north, where the Bedford Institute used to go back every year and do a survey, and they put it all together and produced a magnetic anomaly contour map. And I was on sabbatical there, and Bosco and Karalik and I wrote a paper on this. Well, anyway, the fit isn't particularly good, but everybody believes, well, of course, the profiles are still telling you something about the magnetic anomaly immediately under the ship. It must be telling you something. What can go wrong? Well, the answer is plenty. If you see there the green function relationship between magnetization, that's M, and the magnetic field it produces, that's B. And the thing about the green function is that it falls off only like 1 over r cubed. The volume of a thin shell around the observation point goes like 4 pi r squared dr. And so, if you take those two things together and integrate, you find that their product decays over like 1 over r, and that interval is like log r, which means, practically speaking, that the even moderately magnetized units of magnetization, if they're large enough, can have a very big effect on the local field. And so you're not really getting a very localized picture. I mean, you like to think of your magnetic field as coming immediately from very close to where you're doing your observations, but because of the slow decay of the green function, in fact, it's not the case. You're getting influence from very far away, and so you may not be seeing what you think has been concentrated average immediately around the magnetometer. Now, to show this is not just hypothetical, when deep sea drilling penetrated the volcanic layer, and still, the cores are subjected to an intense scrutiny with paleomagnetism, very time consuming. And someone suggested, which I think it may have been Ken McDonald, that what you need to do is pass the magnetometer down the borehole, and that will tell you what the profile of magnetization is. All you just need is a transfer function between the magnetization in a volume and the magnetic anomaly. And so my friend Jeff Daniel, who was on sabbatical at IGPP at the time, and I decided to analyze this problem. I want to say, well, what can you say about magnetization around a borehole from magnetometers going through it? And instead, we couldn't use a model as simple as the Vine-Matthews blocks. We decided to use a somewhat more sophisticated model, a statistical model of the magnetization vector M. And so we chose a model in which the magnetization was a realization of a stationary stochastic process in 3 dimensions, vector value 2, making it even more complicated. This is a generalization of the power spectral analysis of time series, which most of you are more familiar with. And the idea is that you look at the magnetization in 3 dimensions as being a superposition of random waves. So that instead, the independent variable, instead of just being time or frequency, is wave number, which is a vector quantity, and the reciprocal of wave number is a wavelength. And so you use as your fundamental measure of what the behavior of magnetization is the power spectral density well known. I'm going to give you a few examples of what this means. So if you have a 2D power spectrum, this has two peaks, one on either side of the origin like that, equally spaced, two delta functions. That's simply a plane wave moving, goes through the system like that. And all the energy is a single wavelength. And now this is a much more sophisticated one. If the spectrum is circularly symmetric, power spectrum, then there's no preferred direction, and you get this rather chaotic looking thing here. All these things are just produced by using the Gaussian random number generator and the spectrum on the right. And you see that sort of homogeneous, that's homogeneous sort of chaotic system. And now, if you have an elongated spectrum like that with elliptic contours, then the strike of the random realization on the left is perpendicular to the long axis of the power spectrum. Now, if that's beginning to look a little bit like magnetic anomalies, that's no coincidence. Here is the survey of 45 degrees north, the Mid-Atlantic Ridge, that paper did earlier. And there's a contour map of a region, and beneath it is a random number simulation with the same parameters and the same strike. And I think you'll say that they're not exactly the same, but the relationship between the two, the random number simulation and the actual ridge, is really rather good, except for the fact that the ridge is a special place, whereas there's no special place in the stationary stochastic process. Every place in the stationary stochastic process has exactly the same properties. So it can't, the simulation can't produce a ridge like that. But on the other hand, the general overall impression here of this simulation is really rather good. So if you want to say we're going to use this as a model for predicting things about measurements, I think most people will say, well, that's a pretty good model. It's a lot better than just uniform blocks. So, onward. Back to Warham magnetometry. We want to know how well a signal measured by a magnetometer reflects the average local magnetization around the instrument. And now we're going to do something a little bit more complicated, because you need to take into effect the fact that the magnetization is a vector. And so what you have to have is a magnetization spectral tensor, a function of a three-dimensional wave number. This is obviously very, very complicated. What can we say we know about this function, gamma? And the answer is pretty much not anything. So we can assume what we like in order to make the math simpler. And that's what I did. Well, onward. The power spectrum tensor is the three-dimensional Fourier transform of the magnetization or covariance tensor. And well, there's the math. There's the integrated problem. Terrible. Okay, so the model we studied was this. You will consider an magnetometer passing through down a borehole. And you say, let's suppose we know gamma alpha beta. And what can we say about the average magnetization in the rocks immediately around the magnetometer? And we chose an averaging region that was cylindrical rather than spherical, because that does simplify the math a bit. And so that's the picture. Imagine this magnetometer going down the borehole and taking continuous readings, and you want to say, what does that signal look like? And then how does it compare with the average magnetization in that cylinder, which goes down and height we can change. And as I said earlier, we don't really have much of a clue as what gamma really looks like. So we make up a model, sort of Gaussian model of the spectral tensor. Well, here's the result of a lot of integrations, which I'm not showing you. Lots and lots of messy Bessel functions, which I really enjoyed integrating. Here's the result. The thing you see there is the coherence spectrum as a function of wavelength. Now, coherence is essentially, at least in this context, is the correlation coefficient between the signal of the magnetometer giving out and the average magnetization which we're trying to discover. And if the coherence is the correlation coefficient, well, as you can see, the correlation coefficient hardly rises above, well, about 0.8 is the maximum, and average altogether. It's not a very good coherence at all. And to give you an idea, there's a simulation. The blue curve is the magnetic anomaly measured by the magnetometer, and the one below is the actual magnetization. That would take a really good interpreter of magnetic anomalies to connect those two things together. So you can see that with this very low coherence, this very poor coherence spectrum, the signal coming from the magnetometer down the borehole will be telling almost nothing about the actual rock magnetization in a cylinder around the magnetometer, which is what you want to know. Well, that used the averaging values that was optimal, so all those are worse. And one thing that model didn't have was significant stratification. And if you put in horizontal stratification, what you get is a lot better coherence. Anyway, so if you start off from the assumption that you don't really know the autocovariance function, you really can't say that what the magnetometer is giving you is a picture of an average magnetization. And borehole magnetometers do not comply with the ESTB procedure. I'm quite certain that paper had nothing to do with that. Okay, so here we have an example where you might expect a magnetometer to go down a hole would produce you exactly the kind of information you'd like, the magnetization in the surrounding medium. But it doesn't unless there are particular specific properties of the distribution magnetization. Well, now could the same disturbing conclusion apply to marine magnetic anomalies? If that was so, that would mean that you're just essentially imposing on the geology your assumptions, which have oversimplified and produced this great picture. Well, anyway, in 1997, Jeff Gee, who's going to be moderating this section, was writing a paper with Dennis Kent and saying they want to analyze the magnetic anomaly obtained on a path that runs right over the parallel to the ridge. Now you see that's a rather strange situation, completely perpendicular to the normal surveys. And so I decided to look, using this kind of theory, to see if it's likely that the magnetic anomalies are telling you anything about the magnetization under the ship, using the same thing that we've done for the borehole. And choose the same model, a stationary stochastic process with an elongated spectrum to give you the stripes. And in this case, we can, I made a simplification, there's the model. The variations are all in 2D. I just assumed the layer was thin enough that didn't need to put in the variation of depth. And so I assumed the magnetization was a stochastic, 2D stochastic process like that. Oh yes, there are lots of surface surveys for which you can get some actual statistical and actually estimate the power spectrum and it's possible to get a rather nice analytical model that fits the data rather well. And so this is the power spectrum. It's elliptical, so it has an elongation, and so it's obviously simulates the stripes. It's a power law spectrum, which means it's a fractal process which has no definite intrinsic scale to associate with it. And you can fit the two parameters, kappa and mu, to the data, and it usually comes up a pretty good fit. Let's see, give you a close picture of that. But anyway, there's the spectrum, and there beneath it is a random simulation. And this is for the East Pacific Rise, parameters for East Pacific Rise. And so that's a rather jagged, not particularly good example of anomaly map. But anyway, there's a simulation. Well, and then from that model, you can calculate the coherence spectrum between the magnetic anomaly and the magnetization immediately underneath the ship. And there it is. And it's amazingly good. The coherence is larger than 0.9 over a long wavelength band, which is what you normally want, what he wanted to do, going along about 1,000 kilometers of East Pacific Rise. The very long wavelengths are very strongly correlated with the magnetization of the ship. But you can't get any information at all, really, at the length scale of tens of kilometers. Coherence is far too low for that. And then the other thing you can do, of course, having done this service for Jeff King and his head, was just to turn the thing around and see what you get if you run your survey across strike, as most surveys are. What kind of coherence do you get for that in this model? Oops. Well, you get this, and it's interesting how different it is. It has no long wavelength coherence, but the coherence is in the range of 100 to 10 kilometers, very good, which is exactly what you need for marine magnetics. So by great fortune, the coherency, the structure of anomalies agrees with the normal prejudice that what you're seeing in the magnetometer tells you something you immediately need to think about. It didn't have to be that way, but it is. And I mean, that's remarkable, how lucky we were. So that's basically my talk. You all knew this was right, but now I've proved it.